talking.
My biology's not far away. I mean, just like mindset. Like, I had to kick Gupta off of this. I have to get myself onto this. It all sucks.
I have an arm. Do you not have an arm?
How is goodness of fit chi squared?
This one may or may not be stronger. They look the same.
Yeah. It wasn't. I do that a lot.
What did you do?
I worked really hard on math for a really long time. We tried to do BC Calc over the summer. We spent some time. I feel like, I mean, I'm not going to say he works harder than you, Carter. Not going to say it. Not going to say he works harder than either of you. But like, I feel like a lot of people who do well in math tend to not put a lot of time into the homework and whatever. And like he does every assignment, as I suspect you do. I mean, just what was in the AI class, which was nothing last year, right? Yeah, he learned it all. Okay, carbohydrates have the general formula C something, H2O something else. They need not be equal. That's where we get the word carbohydrate, because they got carbo and water. They have to have 3 or more carbons to be considered carbohydrates. So methanol, which is CH2O, if you're not ready to talk organic, is not considered a carbohydrate because it's just one C. It has to have 3 C's. One of those O's has to be a double bond. It has to be either a ketone or an aldehyde. Haworth projections are the way that everyone in this room likely draws a sugar. If you draw that flat hexagon, that's a Haworth projection. We just have a fancy word for it. Margaret's going to be able to say that the reason that we draw it that way is because it's pretty easy to look at. It's not accurate. It's not a planar structure. It's just like it shows the information pretty straightforwardly. They're all bends. 109-degree angles. I don't know. Depending on how much time we have, I thought about making them. I don't know. Wang did this whole unit in 20 minutes, and I was like, I don't know how to do that. So
You said that they have to have at least 3 carbons and one of the plastic connected to the whole bond of oxygen.
yeah. We're going to divide sugars into some classes, so we'll talk about pentoses and hexoses. That is 5-carbon and 6-carbon sugars. What's your favorite 6-carbon sugar? What's your favorite 5-carbon sugar? Well done, everybody. Ribose and glucose. We're also going to break them into aldoses and ketoses. What's your favorite aldose?
What is an aldose?
One that has an aldehyde. Glucose. What's your favorite ketose? Fructose. We'll see pictures of them later. You don't have to know that. I just don't know what you know from that other class you take. So many of you. So it ends up that sugars are complicated molecules, like really complicated. And I'm so sorry. Super sorry. I was reading about ribose. I was like, holy moly, ribose is a lot. So most sugars appear in 3 forms, but ribose does even more than that. So that's why I say it's even more cool. I think this is just on the internet and not in our syllabus. I, again, was just reading about it today. So if I were to draw you glucose, you're going to draw 6 carbons in a row because it's a hexose. If you ever wish you had nitrile gloves, you know that's where I'm at. $200 worth of gloves. both bigger and smaller than I imagined it would be.
You printed like all of you,
No, Miss Peters. So Miss Peters has a stack of like 100 of them. Because, like for the real test, we spend the day in between the two, like the afternoon in between the two exams going through them to make sure you didn't mark it up. And that sucks. And so I think that for the exam, she always prints a new set so that we know they're clean on the way in. Then we check them on the way out, but she doesn't like reuse them very often. I don't know, she has a lot. She has a lot. Okay, so I'm looking for glucose so that you guys don't think I'm a big liar. It's table number 34, or entry number 34, it's not much of a table. It's page 33, table 34. And so I told you to put 6 carbons in a row to call it glucose. Glucose is an aldose. You can see that it has an aldehyde at one end. You can see fructose on the other side of it does not have an aldehyde. It instead has a ketone, so it's called a ketose. What I know about glucose is the third OH is on the wrong side. I don't know what you know about it. Okay, so that's called straight chain glucose, but that's not the picture that you guys were picturing when I told you to draw glucose, right? And so it ends up in water. You have this, and this is only, so there's an equilibrium established. And the equilibrium is established between this, which is about 1% of the time, this. And there's not really strong advantages between these two. But this is the difference between what we call alpha and what we call beta. It's which way the ring comes together. It's going to affect the interactions around one carbon center. So when this thing folds up, this O is going to bond to that C, that's C number 1. This H is going to bond to that O, it's going to become an OH. But again, because it can do this 2 different ways, we have 2 different potential products. Lord knows if I did this right. This product with the OH on the bottom on carbon number 1, this is called alpha glucose. If the ring forms the other way, so instead of sort of bending around this way, it bended around that way. Because we have 1, 2, 3, 4 chiral carbons, the bending does matter quite a lot. We would simply flip the order of those 2, and we would refer to it as beta glucose. When we start counting a sugar, we look for this oxygen. It's really this oxygen here, and that is carbon number 1. That is officially a nucleophilic addition reaction, an intramolecular one. We don't need to know the mechanism. Difference should be here, carbon number 1.
What's the difference? So the O bonds to either one.
So that's why I keep doing it with my hands. Like, this part is chiral, so it is sided, right? And so if the chain comes together this way, it is a fundamentally different molecule than if the chain comes together this way, because I'm either facing out or into the ring. And the way that we see that in the Hayworth projection, which kind of hides chirality, is simply by seeing that this particular carbon changes its stereochemistry. So that's like me facing into or out of the ring. I don't know. The only difference is right here. If we want to take a monosaccharide and turn it into a polysaccharide, we've got to make bonds between them. We're going to make a condensation reaction occur. We're going to lose a water, and we're going to call that bond a glycosidic bond. I had a cute phrase, it was P for why we do carbohydrates. Oh, yeah, P. They're precursors for lots of molecules. They're energy and stores and energy reserves. I don't know how those two things are different. It's both a fast and slow source of energy. P. Okay, I made it up this morning. You don't have to judge me so harshly. Are these the no. The hardest thing for me in this unit is to draw a disaccharide given two monosaccharides. You might remember on a homework assignment weeks and weeks ago you had to draw sucrose. That was hard. I don't think this part is hard. Relationship of the properties and functions of mono and polysaccharides to their chemical structures. Not sure what it means, but I'm not worried about it. I feel like I should know what that means. I have no idea what it means. Officially unworried. We talked about how carbohydrates contain less energy than their fat brothers. That's because they contain a whole lot more oxygen, so they're already partially oxidized. We talked about how they have the general formula, CXH2OY, where X is bigger than 3. Some of you are thinking, oh, in DNA we lose an OH. We still think of deoxyribose as a sugar. We still call it OS, but it does not follow this formula. And so that's why it's got this, like, this language. Like, we got you. Traditionally, we refer to them as mono, di, and poly. We don't really talk about trisaccharides very much. Raffinose is a trisaccharide. Raffinose is what Beano tries to break down. So if you ever have noticed that beans give you intestinal discomfort and they make a drug to help you solve that problem because they ferment in your gut, you can't actually break down the bonds between the sugars very effectively. It's some of those oligosaccharides, if you want a fancy word, that are causing that discomfort. So the bacteria in your gut are able to process them, making gas, but your stomach is not very efficient at breaking them down. Beano is an enzyme to break some of those glycosidic bonds. Raffinose.
Why are you so? I just don't get it. I don't know why. It's making me mad that I don't get it.
This projection is known as a Fisher projection, I think. Newman projection, Fisher projection, Newman. That's known as a Fisher projection. How nice for you. It looks like a fish. This is actually meant to convey some notion of stereochemistry. It's kind of terrifying, and we'll talk about that in B10 or something. But the sidedness here matters. So if you decide that you want to go all artistic and line up all the OHs on one side, you've drawn a different molecule. So the placement in this picture is extremely important because the stereochemistry is implied in the picture. We would refer to this as a 1, 2, 3, 4, 5, 6 carbon sugar. So that's a hexose, it's an aldose. This, on the other hand, is a ketose, but it still has a 6 carbon chain. so it's still gonna be a hexose. I hope they ask me all the hard questions about that. Like Mr. Payne wrote these slides. Yeah, thank you. I sure can. So you're gonna see that the only difference between glucose and galactose is gonna be the orientation around this carbon. Here the OH is on the right, here the OH is on the left. No, I'm just trying to stall for time. So it's fundamentally a different molecule, right? Two glucoses in a row is maltose, a glucose and a lactose is a glucose and a galactose is a lactose. All of these are monosaccharides, but just the placement matters very much, so you have to believe them.
So placement matters because of the
Yes, ma'am.
that's like the difference between the OH being like on one side versus the other.
Yes, ma'am. Okay, this slide really just says aldose and ketose. Aldose, ketose, aldose. Some of you might know that if you draw glucose and galactose, it will look like a hexagon in the Haworth projection. If you draw fructose, it looks like a pentagon. That's because this is in a different place. So when this comes up to meet it, it leaves another CH2OH group.
It's not a Fisher projection? Or is that-
This is a Fisher projection.
And the Hayward one is like.
The Haworth one is the one that looks like this. Like, I think if I were better at it, I would draw this coming towards you. I think this is officially Haworth. Haworth doesn't have a Y, but it's pronounced like we all wish it did. Alright. Do the presence of the carbonyl group and the hydroxyl group. We can do an intermolecular nucleophilic addition reaction. Last I checked, that's not in our syllabus. You have electrophilic addition, you have nucleophilic substitution. In the old syllabus, nucleophilic addition was assessed. It's not in this syllabus. So they talk about it like maybe you know something about it, but you do not. So there's nothing to worry about here. This is not a question that's gonna come up. This is not a synthesis question. But what I was reminding those of you who know it of is that when this one folds up, it does look like a hexagon. When this one folds up, it does look like a hexagon. These are both aldoses. If you shift the position of that to make it a ketone, now it is going to look instead like a pentagon, and it has two carbons hanging off. Where this carbon is the new one that you see right there. Good.
In the drawing of glucose on the left, it's OH, H, OH, 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 but in the lineage room, it's OH, H, OH, H. Is it matter? Is this pyridinose?
Yeah, it says Pyranose form. I don't know why.
So that.
I drew the one that's in your. I drew the one that's in your data booklet, so I drew the right one.
Okay, and so the difference between glucose and galactose is that, okay, it's swapping.
We call these epimers of each other, or diastereomers, saying that they have like a chirality shift, but that's all. I don't know why they're different.
So that's what you drew on the
No.
Oh,
This is glucose, that is glucose. Everything I have drawn is glucose. The two pictures on that board are in the data booklet. That is straight chain glucose and alpha glucose. The only thing that you would have to intuit is what is beta glucose. Beta glucose is when you take carbon number 1 and you flip it. So it's always carbon 1, it's because of how the ring closes. That's the only thing you would have to deduce here. Again, don't know how he did this in 10 minutes. I've said those words. Apparently we'll talk more about alpha and beta in B10, that is the stereochemistry HL part of this. I would like to make that part as short as possible and this part slightly and painfully longer. You think it's bad now, after spring break y'all are going to be even more useless. Okay, this is a lazy person drawing sugar. If you drew sugar like this, would you get any marks?
No.
No, because you must show all hydrogens. So again, this is called a Hayworth projection. You can see that this shading is officially present in a Hayworth projection, trying to say that this is coming toward you, and this is receding back behind the plane of the paper. From the straight chain. Traditionally, we do not.
Or like the shaded.
Yes.
We do.
I would know, I mean, again, the picture's right here. And if you don't like that picture, there are more pictures. So they have pictures of fructose, ribose, and deoxyribose. So I think the question is typically why do we do this, not how do we do this. Glucose is the most common monosaccharide. It's what we use for energy. It's what plants make for energy. Yay, plants. We can ferment it to make alcohol. I feel like I recently was talking about that.
Oh, anaerobic further.
B1 in biology is all about fermentation and reactors. I had fun too. I don't know what a reasonable question could possibly look like. So can we write this equation? Write a symbol equation for this process, glucose. Making alcohol. Do you think I need pyruvate? I really don't want to have pyruvate. I don't think I'm good enough to do that. I'm not good enough to do this either. How much CO2 am I going to make? That don't make sense. Yeah, I chose 6 because I was trying to use all the carbons. It doesn't make sense. Just watch. Okay, here's how we're gonna rock it. So y'all are telling me I forgot CO2. You're right, I forgot CO2. Let's go. So I think I've got to do something like that. So I decided to put oxidation states on everything. I knew that the oxidation state in glucose was 0, so I just started there. I was thinking that the oxidation state in ethanol was 0 when I was writing it, so I was so nervous about the CO2. Totally right, so I calculated it instead of assuming it. I have -2 and +6, so this counts to +4, so each of these is -2. So a carbon going from here to here is going to have to gain 2 electrons. A carbon going from here to here is going to have to lose 4, because of course it's 4 there. So I need this reaction to happen twice as often as that one. So I believe it is right now. think so. So I have 6 carbons on both sides, so no one's gonna shame me about that. I have 12 hydrogens on both sides, so that seems appealing, and I have 6 oxygens on both sides. So we have balanced it using the magic of oxidation reduction numbers, because I'm not smart enough to know biology. Like I could have written that down, I'm sorry, I don't know if I didn't mean to let you down, I just don't know.
Do you have to do like all the oxidation reduction stuff?
I just didn't know the reaction.
Oh, okay, that's.
I just don't know it. I'm showing you how I came up with it without knowing it, because I don't know it. But you know it. Keep knowing it, dude.
Wait.
Yes, sir. Have you guys used a failing solution or Benedict or Benedict?
For the maltose, yeah, we need to break down maltose. Let's get with the plastic bag.
What color is Benedict?
Dark.
Is it blue? Is it dark? Dark blue. Yellow's the ice cream. No. Is it true? They have different colors.
No, my mind, that's what you.
Are you unfamiliar with them?
So there's a test we can do to help identify sugars. What it does specifically is identify reducing sugars. So that sugar is an aldose. I know that because it has an aldehyde in it. But I know that aldehydes can be oxidized into carboxylic acid. So we refer to aldose sugars as reducing sugars because they can be oxidized, they can act as reducing agents. And so if you put copper 2 into a solution with a reducing sugar, the copper 2 is in fact reduced to copper 1. We don't normally talk about copper 1, but it forms an orange-red precipitate.
Oh, so Benedict's solution is actually
Copper sulfate and some other jazz, but yes. Because Biuret is also copper sulfate, like the jazz is different.
How often is copper 1?
This is the only case I know of making copper 1 on purpose.
Okay, I've never seen that.
So it all depends on if you have an aldose or a ketose. Aldose is like glucose or reducing sugars because they have that aldehyde that can be oxidized. This seems straightforward, but the more you read about it, the more you're going to know it's not straightforward. So that is an example of the color change. So this is the Benedict solution. It doesn't say before, and that's the Benedict solution after the orange-red precipitate. You can also use failing solution to do this. So as Audrey was saying, copper sulfate is the main ingredient. I was talking about the other jazz because I don't know what it is. Sodium potassium tartrate and sodium hydroxide in this case. You don't need to know that. 100% don't need to know that. But you do need to know that the blue solution will form a red precipitate in the presence of a reducing sugar. What's complicated is that sucrose acts as a reducing sugar and it probably shouldn't. And that's because the molecules can do all sorts of complicated things in water. So it just ain't nothing easy. All of biochemistry is hard. Trying to be patient. So you can imagine that some of you did IAs where you were looking at the amount of glucose that was produced, and you used glucose test strips. No one did that this year. Usually I have to buy like hundreds of glucose test strips. This is a way that you could do it spectrophotometrically. It actually depends on how much of that copper 1 you make, exactly the color of the precipitate. As the precipitate gets bigger, it turns from red into kind of a yellowier color. So you can take photos of it and sort of quantify something that's not biology. Don't write this down, please. The reason this is a right pain in the ass is because glucose in the presence of base can actually turn into fructose. That's a real bummer because now we've taken a sugar, like fructose, that should not be a reducing sugar, but we've turned it into one that can be. And so you can get some false positive tests from things like fructose because of this intermolecular, I call it tautomerization, but I might regret saying that word out loud. So there is an isomerization in the presence of base that allows fructose to turn into glucose. This will test positive in failings because we could oxidize that. Similarly, I was trying to woo you with Benedict. In Benedict, depending on how much is present, you can change the color of that precipitate. The IA's been done. Okay, Langenlit people, let's analyze this. What are we trying to learn?
There are uses of primary colors.
This is something. So the color.
The black and white
Which one are we in?
provides stark contrast.
You've never watched the documentary King Corn on Netflix? It's quite
The
interesting.
contrast of his legs and abnormally wide torso.
The position of his children at the bottom have a more high perspective compared to the other men shows their
It's a
lower
position
position in
of
the
power.
social hierarchy.
Exactly.
You're just saying juxtaposed, it doesn't make sense.
The threatening aura is emphasized by the direction of light present, seen in the shadows.
What's the word, his caricature, or?
The characterization,
No, not the caricature. The caricature nature of his large nose shows his intent to lie in terms of
What did
how
he say?
how he presents information about food.
She's drunk, that's the alcohol red nose.
So is he using?
I'm gonna fight you on that one.
Does the back say corn?
Yes, it's corn.
Can you make
Yes. So the reason that we use corn is to make ethanol, which is an additive in fuel. So if you go to Buc-ee's, right, it says no more than 10% ethanol in this fuel.
But what does he say?
Pardon me, but do you have any?
Pardon me, do you have any food? He's dumping ethanol into a trough for the cars.
Is that
Oh,
like?
sorry, he's dumping corn into a trough that's labeled ethanol for the cars.
This comment.
This says corn, something, biofuels. Oh no, you can't eat this. This is to make ethanol so I can power my SUV. Oh, yes, yes.
Where's the wrong one on the bottom?
Ethanol is
Looks like a
Hog
spray.
farmers, chicken farmers, food producers, dairy farmers,
The
ethanol.
way that they're holding it looks like a spine.
It's a
So it's a corn stalk and they're playing that game where you have like a stick and everyone puts their hand up and you want to be the last person holding the stick.
It's like a weird, like,
Oh, so those are hands.
Yes, these are, all the different hands are grabbing
I
up
see
and
the
playing.
sleeve.
I think so.
Why
The,
do
the hands themselves look like vertebrae.
Yes, they do.
Is that what, is that important?
I
Corn
don't
is the
know.
backbone of
If
society.
I were right
Think of all
playing
the
it, it would
industries
be.
that have it.
Ethanol is the drink.
Ethanol is the drinking alcohol, that's why I think he's drunk. It really is.
therefore, the hands are the vertebrae, as everyone, all the
There you go.
industries are trying to grab at.
To give you a statistic I've learned in the last 12 hours, the amount of corn it takes to make 21.6 gallons of gasoline is calorically equivalent to the amount of food it takes to have someone survive for a year. So like this really is a decision that people are making. Most corn is not food. Most corn is gasoline.
Is there no other organic compound that can substitute?
It's just really cheap.
People are hungry.
I'm not saying it's
They
right.
don't care
I'm just
enough.
saying, like, in terms of substitutes, I don't think they have found a more cost-effective one. I think we also make so much of it that it's probably not possible to get it to people fast enough for them to eat it. So I think you have to find a way to make it have the same longevity that gasoline has. We have the infrastructure to store that. It's fun. So when disaccharides or when two saccharides come together to make a disaccharide baby. So here we have two glucoses. This is the carbon 1, this is the carbon 4. We're going to make a alpha 1,4 linkage. Remember, alpha tells me where this OH is. If it were beta, it would be on the top, so that alpha is important. This is carbon number 1. He's bonding to carbon number 4 on his neighbor. That molecule is maltose. This is called a glycosidic bond or glycosidic linkage. Looks a lot like a ether. The picture is really bad. So how many carbons are in between here and here? So I'm taking this carbon and I'm asking the question, in maltose, what's in between them? Not like a trick question. What? So I believe that this is a hydrolysis reaction, so I'm gonna lose the water, and that oxygen is gonna bind to both of these things. All that is between these two carbons is one oxygen, but like at least half the people in this world draw it like this. When we have a vertex in an organic molecule, we typically read that as a carbon. There is not a carbon here. It is a very poopy thing.
So there is no.
There is no carbon there. It is frequently drawn like this, but it should be drawn like that. Carbons in the hexagons are directly bonded to an oxygen. It's just a misleading drawing. It helps to make cellulose if you draw it this way. That's why it's done, but it's not effective if it's confusing. So I just want you to understand that the glycosidic linkage is just an oxygen. There aren't two random new carbons. Perhaps the things that confuse me are not the things that confuse you. Here we have glucose again. Here we have fructose, and as in your homework, they've made a link between them to form the disaccharide sucrose. Because both of these structures are in your data booklet, this is by far the most challenging disaccharide to draw, so if Margaret's in the mood to make flashy cards, this is something I would put on a biochemistry flashcard. If she's not in the mood, that's also okay. She is going to get most of the marks for knowing that there is a glycosidic linkage. Again, carbon in the ring, oxygen, carbon in the ring, and then she's going to lose water. All of these reactions are condensation reactions.
So 1, 2, or 1, 4?
This one is 1, 2.
So what's the other one a different thing?
But that was from the maltose.
Oh, okay.
The way it is configured in the data booklet is not the easiest way to make these two things come together. You can look at it in the data booklet, it's on page 34. When you look at it in the data booklet, you're going to notice that the carbon that is closest to where you would have the OH that's going to be lost on glucose is not the carbon that you're bonding to. The carbon that you're bonding to is somewhere else. It's just not convenient. Yes. And that's fine. That's why I'm saying, like, I would just have to write this down. It's not something I can do this with the aid of the internet, but I don't know. Galactose and glucose come together. This is a beta 1,4 link. Beta again means that the OH is on the top instead of the bottom. So we have the 1 here, we have the 4 there. We're going to link from the beta 1 on galactose to the 4 on glucose. This is lactose. You do not need to know that that is lactose. You need to just understand that this is yet another hydrolysis reaction, and if someone told you that you've gotta link the 1 to the 4, we're not gonna try to do a great 3D drawing, we're not gonna try to show what angles these are, but we are gonna show that it's gotta be this OH and this OH that are somehow losing that water. So this molecule will be unchanged, that molecule will be unchanged, and I'm just randomly gonna string a line between them and not try to overcomplicate it.
Will we be asked, sorry,
No.
will we be asked to draw this?
Yes, there is a real chance you would be asked to draw it.
All three of the examples so far could show up, or just?
Sucrose has shown up, so I hope it never shows up again. Maltose is the one you're praying for, it's easy.
So, alpha, beta, one more, that's the difference.
The OH on top is beta, the OH on bottom is alpha.
Yeah. But, drawing is from
Like, I'm looking for the OH, I don't understand, I'm looking for the H. Like, I'm missing what you're saying.
if you're drawing a dot track, right?
Yeah. No, so I was challenged, because I don't know how to answer this question, and I hope Amaranth is much easier. To draw a beta linkage between two glucoses, so this is gonna be a fragment of the molecule cellulose. So if I had to do this traditionally, what is done, because it's surprisingly hard to do, is I'm gonna take this OH and this OH, and I actually draw something that looks like that. There is no carbon here, there is no carbon there, that is a common shorthand that's used in textbooks. If you wanna draw something that is not ridiculous, you actually have to flip this molecule over. I think they would have to give you some reasonable instructions to do that, or I would just lose the mark. I would get everything else, I would draw this, which is common, hope it's worth it, and then throw it away. The time it is gonna take me to figure out how to flip this molecule over on a test is like way more than the minute and a half it's gonna be worth.
You drew it on like your periodic table, with a separate tissue paper, and flip the paper over, and then copied that down, is that flipping it?
We have to mirror plane it, so you have to flip
Oh,
it.
never mind, never mind.
Oh, actually, you have to flip it this way. Arashi, what you got? I failed these two.
I'm just asking, so sucrose, it's a combination of, is it still a 1-4 linkage?
It is not, it's a 1-2 linkage.
Beta or alpha?
Alpha, I'm relatively sure.
Alpha linkage between two glucoses?
No, between a glucose and a fructose. I have not lied to you, I double checked while we were talking. It's on the previous one, sorry. It's just impossible to read. That's an alpha glucose, that's a beta fructose for what it's worth. But this is carbon 1 and that's carbon 2, so it is a 1-2 linkage with a beta glucose. Emma, I feel like you had a question. Nothing but surprise. Okay.
Does the P mean anything?
Yes,
Or,
yes, but not till B10. Sorry, there's a limit as to how much joy I can bring you in one day, and the limit has nearly been exceeded. I'm not ready for that.
Is the lactose always gonna be the beta, like, lactose?
I think so, but they did refer to it as beta lactose. I am unfamiliar with there being 2 different isomers of lactose, but I am not.
So the H's cannot be like both down. Like say like that other H is like down there. Yeah, they can't be both down there.
I mean, in some molecule they could be. So like that would be totally reasonable.
Does that change like one, like, are they both still beta?
No, this is a fundamentally different sugar.
Okay.
So alpha and beta is just changing a carbon 1 where I have some freedom because the ring can close either way. If you change it a different carbon, it's no longer glucose, it it's lactose, galactose, it's, name another sugar, I'm not good at this game. So it's like fundamentally different. Boronose, I was reading about boronose last night, that's one of the sugars in the peptidoglycan chain. Boronose. No. You need to memorize the structures of zero sugars.
Just to clarify, lactose, a beta one
Lactose is a beta 1,4 linkage.
and then sucrose is alpha one.
Yes, ma'am.
Are the glucose and galactose and lactose any like particular, are they like alpha?
They're both beta.
Beta?
And so Mohab's question, and the question I don't know the answer to, is the glucose being beta is deciding where this is. That's what's making the lactose beta, is deciding what this is. I don't know if it's possible to own alpha lactose. It doesn't matter in terms of me drawing this linkage, and so I'm just gonna draw it with whatever molecule they give me. Like, it makes no difference at all. This one would matter, this one does not matter, so I just don't know. I don't have a reason it shouldn't exist, I've just never heard anyone speak of it.
These slides will be on campus.
Yeah, slides will be on campus. So disaccharides can unring. Super sorry for that. So I have two glucoses together here in maltose. I've left the glycosidic linkage there, but I've reformed the aldose. That means that maltose is also a reducing sugar. That means that this would take the copper 2 ions and turn them red. So again, that whole notion of reducing sugar, it's great, but it seems like most sugars reduce. Remember, fructose shouldn't, but it can isomerize into glucose, which does. Sucrose, we thought we were out of the woods because at least we have this disaccharide now, and certainly they wouldn't keep talking about it, but it can ring open here. That would support Mohab and Amarachi talking about an alpha and beta glucose. If that ring can in fact open, it could close. I mean, some sugars do fail, it's just more past than you would expect. Writing this, I don't know what she's writing, so nervous about her notes, but she's gonna sell them to me at the end of the year. I mean, they're beautiful. You ready to go for pub? Here, let's look at this, I'm just scared what it's gonna say. Oh, sucrose, we already drew that, good, skipping. Polysaccharides is when we have more than two. It's actually two or more, but we have like a special affinity for disaccharides because sucrose and lactose are things that we talk about with each other sometimes. So we're going to talk about the 3 polymer structures of saccharides, maybe 4. Can you name any of them?
What? One sucker?
Polysaccharides. Okay. Well done. Here's amylose. Amylose is a string of alpha glucoses, all with 1,4 linkages. So if I only had 2, we call that maltose. When we make this string really long, we call it amylose. Amylose is the easiest for our bodies to break down. It is the one that turns the starch triiodide complex that my kids are looking at black.
So maltose is white,
Yes.
amylase,
Amylase in your mouth and in your pancreas.
2 maltose, 1 glucose. Is that what we're talking?
Where's my pancreas?
Here, this your pancreas.
One of you saying it's on the right, one of you saying it's on the left.
It's on the right.
Oh, it's on the right.
It's on your right.
Your right. Your stomach is on the left.
Yeah, so that's on your right.
So if amylase broke it down, 2 maltose, 1 glucose, or a 3 image.
Why 3? It's long, it's forever long.
Oh, it's forever long.
It's a polymer, so it just cuts them off one at a time. That's why white bread and white rice taste sweet in our mouth, because we're making their glucose in our mouth as the amylase is breaking them down. So this is a long unbranched chain, all alpha 1,4 linkages. It's in the middle. This is a helical structure, yes. Does it say that yet? I think it's gonna say that later. But you're right. My boy Brecken is right, this actually forms a helix. Huh? Amylose is helical.
Is there a limit to how long these things can be?
Not that I'm aware of. I don't know what the typical length is. But one of them cats was looking up the molar mass of starch yesterday, so like you can find the average length. What they're doing is anyone's freaking guess, but. Amylopectin, by difference, in addition to having these alpha-1,4 linkages, takes another link. There's an alpha-1 here that's going to bond to the carbon-6 down here. One of these sprouts off every 20, 25 units along the chain. So amylopectin is different than amylase only in that we get this branching. Again, every 20 or so saccharides down the chain, we get a branch that is an alpha-1,6 linkage. Remember, if you're looking at this thing, this is carbon number 1, 2, 3, 4, 5. This is carbon number 6. So he's the one who's going to bond right there to this oxygen, which in turn is going to be on this carbon.
With the branch?
Yes, the branch.
That's why pectin's thickening.
So pectin is a thickening agent in jams because it can bind up a ton of water.
So amylopectin is the amylose of the long chains of the 1,4 bonds, but then it branches off when it goes to 1,6.
Yes, ma'am. They're the words. So I would call it alpha-1,4. That's how I read it. No, so I want to know that the alpha, like, I need to know carbon 1 is alpha, and I needed to know it's bonding to number 4 on someone else. 51 minutes in. We don't know what that says. Plants make starch. 80% of the dry mass of staple foods, starch. Yeah. In the presence of enzymes, we break that down into glucose. That feeds you. Since the molecular masses of both amylose and amylopectin are very large, both are often represented as a whole bunch of these and an N. So if you added N waters to this, you could form N saccharides. So that is the hydrolysis. It is in fact acid catalyzed.
Do people, like, do things to find out what the end is, or it just happens?
People do things. So your dialysis tube tells you how much stuff is in water, right? So you can do an osmotic pressure lab to figure out how many there are. Yes, I'm tired too. We have a practice question. I hope it's very interesting. Ooh, it's a calorimetric question. I got all the answers. Do you have all the answers? Can you picture this? So we're gonna burn some starch. We have 2.66 grams of starch. It's gonna heat up some water, and we'd like to find the energy density of this starch. So we admit that different foods have different energy densities, even if there is an average for starch. And so I claim that it's a straightforward calorimetry problem, much like the one on your recent long exam. There are 3 steps to solving it. In step number 1, I need to know how much heat was absorbed by the water. MCAT, so I'm going to take the mass of the water. I'm going to multiply it by the heat capacity of the water. And I'm gonna multiply that by the change in temperature of the water. I now know how much heat the water absorbed. From whence did the heat come?
So,
So burning the starch gave off all of the heat that was absorbed by the water.
Hi.
Just chilling, welcome. And so what would delta H here be?
Q over minus.
Because it's in kilojoules per gram, I'm putting it over mass, just because those are the units that they gave me. And so if you want some numbers, Q is 46.1. Kilojoules. So this is gonna be minus 46.1 kilojoules. I'm gonna divide that by the mass, which I've already lost, 2.66 grams. And I'm gonna get 17. I dropped the minus sign. I don't know how I feel about it. The question is, what is the energy value? I feel like the energy value should be an absolute value. It is an exothermic reaction, that's why it's negative, but that's why I drew this arrow here. I know I dropped a minus sign, I was just trying to answer.
The mark schemes don't accept negative digits
Pretty forgiving. I mean, this is not a real question, what? If someone said, what is the enthalpy of combustion, the answer would be negative. If someone said, how much energy is released, they will typically take both answers.
What was the kind of problem we had on our test? That was like this.
Yes?
What was it? Was it like this?
You made a hand warmer,
Because that one said don't accept negative digits.
but that's because.
I'm just trying to see like what aspect we're on.
It is a different issue than this, I believe. Like, it's because you're in danger of getting negative mass. Like, negative mass is a big no. So that's where they would not accept a negative answer. Reckon. Okay, so the second part of this question seemed like the more interesting one, because this didn't seem particularly interesting. It said, how would this compare to burning a whole lot of starch? A whole lot of sugar. Suggests how the energy value of sucrose and glucose would compare to that of starch. Why does the glycosidic linkage matter? Don't agree with that. I think that's a goodie. I don't know, I have my answer. I can't read ahead far enough to their answer. I just have my answer. What have I lost if I take starch and turn it into sugar? Water. No. No, Karthika, no. You listen to me, but I'm dumb. Okay, so Karthika said the right thing, but I asked the wrong question. Water and starch make sugar. We have to hydrolyze that bond, right? We're not condensing. And so I think what Brecken was saying, but I just didn't like the way he said it, is that the starch is like a dried out version of energy. We don't have to carry the water around. We have to add that water back in to make sugar. But when we burn something, we only make carbon dioxide and water. So taking this water and converting it into water would not give us any energy. So we'd have the mass of the water that we don't want. So its energy density would be lower because it contains all that water. So higher energy density, lower energy density. Barely awake. wish I could find my pretty slides. Okay, you win. Starch and iodide, they make blue-black compound. I would love to. So the way that we defined energy value was the amount of energy we got out per gram. And so what I'm saying is that if I compared starch to sugar, by which I mean a mono or disaccharide, the difference here is that starch is kind of the dehydrated version. Every time I make one of those glycosidic linkages, I lose a water. And so because it's not having the mass associated with that water, every single one of those units is gonna lose like 18 grams. And so the bottom part is going to be smaller for the starch, and consequently it's gonna have a higher energy density. Oh, sugars. Oh, we have 30 minutes. Oh, that's so exciting. Why would I close this? We have so much time. Oh, it's Wednesday. We have 15 minutes.
I have a question.
Yeah, let's make this go faster.
Carbohydrates were P, what did the P stand for?
Precursors. So I was thinking, like, I don't know what they're precursors in us for, but if you think about what vitamin C looks like just like a sugar. It's in your data booklet.
Like precursors to other molecules?
Yes, to other molecules. And so if you look at vitamin C, you can see that like dogs and cats synthesize their own vitamin C from sugars. I think I could argue that the ribose that you make in DNA is like a complicated thing you make out of sugar. So it is a precursor for DNA if I had to come up with something that's not a lie. What? Precursors to other molecules, energy storage, and energy like immediate use. Is how I had 3. I don't know how you guys tolerate these someone else made the slides classes.
Depends on the class.
It's awful.
Irony depends on the
Yeah, you're not handling it well. That's not. What can you tell me about vitamins? Okay, so instead of being a macronutrient, like the things we have been talking about, they're considered a micronutrient. So we need them in much smaller quantity. Like you don't live a long time if you're not eating proteins, fats, and sugars or starches. They're essential. That's how we use it for fatty acids. So they are essential. You cannot make them. You're right, that is part of the definition of vitamins. There are things you cannot make yourself. So vitamin C is a vitamin for us, but not for the dog, because he can make it. What is what? I don't know.
Is calcium a nutrient or a vitamin?
I believe it is a nutrient.
So, I'm thinking of like bone and stuff where, I don't know, I think I'm thinking about it backwards, but like vitamin D and like bone health and stuff, they go hand in hand, but it's not gonna make vitamin D, but like if you're in the sun, like their skin so different, then they won't produce. So does that count? No,
So vitamin D, like I know that I've talked about it before, I know I'm not well prepared for this right now, but the idea is that while your body can make it, it frequently can't make as much as you need. And so because you need to supplement with it, we can call it a vitamin. I think also that the naming of vitamins is extremely archaic. I think we would do a better job had we known the answer before we started, but I think when we were coming up with vitamins, we didn't know the answer, and so that's why there are some letters missing.
true, like, I mean,
Like I had ascorbic acid is vitamin C.
Something like that one.
So yes, they all have like fun organic-y names.
I don't know about vitamin K, but I remember because K is like clotting and stuff like that. So what it does. But I don't
Yes.
know how like that's different.
Me neither.
Oh, the min is from animals. Oh.
How exciting.
I originally thought containers were acids.
So if you look at page 35, you're gonna see 3 vitamins that you guys were just talking about. And you're gonna see that we do have names for them. So we do call vitamin A retinol. It is involved in eyesight. We do call vitamin C ascorbic acid. And I thought vitamin D was like calciferol, but now I'm like trying to find out. Does anyone know?
I have no idea. Why are there like different vitamin Bs? There's B12 and B6.
So what the B's have in common is that they're water soluble. Why didn't we mix them with the C's? I can't tell you. But it was because they had some grossly same properties, most of which was they are water soluble. So you can take as much vitamin B as you want, and if you take a vitamin B supplement and you look at the RDA, it's gonna say like 10,000 times the amount you need. And that's because you just make expensive urine, right? It just passes straight through your body. But vitamin E or D, those are fat soluble. You can actually poison yourself with them. So the reason I asked you to look at page 35 was because a relatively common question is, yo, tell me if this is fat or water soluble. A, D, E,
There's some
K.
or not.
Or fat soluble, not water soluble. Yes. And B and C are water soluble. But the question that Raimi would be answering is, ooh, I see a whole lot of OHs on that ascorbic acid. It could hydrogen bond to water. Why, of course, it's water soluble. Right? We've got to chemistry up the answer. So we know ADEK is the answer, but we have to make it sound compelling. They could throw down a structure of niacin, something that none of us know off the top of our head, but ask you the same question. If you recognize that niacin is B3 or B6, I'm not very good at that, then you'd be like, oh, of course it's water soluble, but you gotta bullshit some chemistry in there and talk about the hydrogen bonding between the molecules.
What they have is
Yes?
Did you say ADEK?
ADEK is not fat soluble. ADEK. ADEK. B and C water soluble. I am unfamiliar with any other vitamins. Some of you have heard of vitamin I.
Does it actually exist?
I've heard like numbers.
Runners frequently call ibuprofen vitamin I. So if you're in a really long race, they'll try to get vitamin I. Yes, so the B's have numbers. So B3 is niacin, B12 is cobalamin, B6 is something that we don't know yet, but she's gonna look it up.
Is it similar to folic? Or is
Oh,
it-
folic acid. Oh, that's B12. Is cobalamin B12?
You search it, it was like colon.
It's cold. That's
Vitamin D is colon calciferol.
Yes. I was trying to say that word. I just don't know how to pronounce it.
There's 2 names.
Ergo calciferol.
Calciferol.
Well, calciferol is like the common thing.
The 2 names are. That's the word I was trying to say.
B6 is pyridoxine.
Pyridoxine. Pyridoxine. Niacin gives you flush. If you take too much of it, you turn red.
Niacin.
Yeah.
What is
Niacin.
niacin?
Is the muscle. Niacin on my eye. You put that in skin.
Niacinamide, yeah.
Oh, I thought niacin.
In the old days, we had to have a table. I hate the vitamin unit even more than I hate some of these other units. We had to have a table of like bad things you get if you don't have enough.
Vitamin C.
C, scurvy.
Yes. I got 1 mark.
I don't have that table anymore, so I think we don't have to do it.
D. You have skin problems.
Yeah, you definitely have skin problems.
Vitamin B12.
B12 is
Yeah.
bone stuff.
The D was
With
not.
B12, I extra
What?
shit.
I thought D was also
You
involved.
cannot.
Yes, it binds up calcium, so.
I had to do research on it for a couple, but lack of B12 can increase your risk of gastritis because it has a relationship with intrinsic factor where like you need B12 to continue producing intrinsic factor. The intrinsic factor like does something for your gut.
Can you dumb this way down and tell me what intrinsic factor is in
I
one?
don't know the technical term for it. I'm pretty sure it's what it's actually called.
Okay.
But it's like in
tried to talk about golden rice the other day. You were looking at golden rice when I walked in here. What you got on golden rice? Which vitamin am I trying to replace? A. What I remember is I got it wrong. So a question that Emma should be worried about is, something about vitamin deficiency. Like, what are some ways of avoiding vitamin deficiency? Eating a balanced diet, I like it. Taking a supplement. So I looked these up because you were talking about them. So thiamine, riboflavin, niacin. No one expects that you know what these things look like, right? No one expects that you know the molecular makeup of any of these that are not specifically drawn. But if you wonder why we call Pantene shampoo Pantene, because it's got that B vitamin in it. Yeah.
The Pantene shampoo has those.
Pantothenics. I think it has some B vitamins. Folate is B9. You were talking about folic acid. That's the one you have to take if you're thinking about having babies. They have you take it early. Prevents some crappy disease. Prevents. No, let's find out. Yeah, it's the neural tube defect. It's like when your spine doesn't close all the way. I don't know what it's called because I'm not feeling clever right now, but you can read fast, right?
Neural tube defect, like the baby's developing and because their spine, because they're connected to like the placenta and stuff, they're just connected to the mom somehow, and because you don't have enough of that, the closure doesn't like close up all the way, so you can actually have like a swelling like full of fluid of like cerebral spinal fluid coming out of your back. It doesn't, yeah. And it looks like an actual like it looks like a stress ball. It's really gross. It looks like a large blister essentially. But it's
The vitamin unit is short. It is not all you need to know, but I was trying to not waste time. I was talking to Margaret about how she felt about videos. I was thinking about the last 2 units in the SL part are really short. That's going to be vitamins and environmental remediation. One guy suggests I make everyone do a project on the different things in the environment, and like I want to poke my eyes out, and you too might want to poke your eyes out because I know you don't have to know like much of anything about host gas chemistry, but I know that you need to know the word, and so if I can do in 15 minutes enough vocabulary so that you can read a question, I thought maybe it would be like a more useful way to practice some of the questions that will be asked in SL so that you suck less of the test, because right now, like the content for the non-biology folk is gross, but for the biology folk, you know all the vocabulary. But the tests are still not going great given the overlap. And so I thought practicing the questions would be good, and I thought if I didn't have to waste your time reading slides about 5 and 6, it would be better. But for carbohydrates, like you have to draw. But for the others, you don't have to draw. So that's why I see them as different. So I thought if I could front load a little bit and make a video, we could be done with 5 and 6, we'd be done with SL before break, practice on Friday, come back. Huh? Practice some actual SL biochemistry paper questions so that we learn better how to answer them on sugars, vitamins, and environment, and perhaps a wheel topper. Yes, xenobiotics is one of the sections in there. So I'm gonna try to make you a video. I don't know exactly when that's gonna happen. But I figure if you have it by Thursday at the end of school, that would be enough time to expect you to watch something that's 20-some minutes long. And the HL topics are gonna come back to sugars because there's lots of stereochemistry in there. They're gonna come back to retinol because they're pigmented. It's gonna, like you're gonna see some of the highlights and things that I'm trying not to talk about too much. Come back to enzymes and the acid-base stuff and maybe if I could make a couple
This-
videos, we could actually do the peroxidase lab, which I think is kind of fun. But also, I kind of don't want to do a lot.
Yes, I've used something like that, whatever brand it is. Yes.
Welcome to
I've
class,
used the
Raby.
great different ones. Same, like this brand, but different.
I don't know how he's getting it better, honestly.
Conditioner.
Bio, we did adoption, we had,
Yeah, that's all I use. I don't know.
lotion, what the top one conditioner, and then I went online, and I was like,
Competitive, we say competitive in my culture. You can say whatever you want to say, okay? We pronounce it competitive in my house.
so anyways, I was searching the question online, and then it